Other causes also promote the stability of nuclides. Let us mention the size of the dodecahedral layers, which shows that the third layer remains more rigid and limits the number of stable isotopes. On the other hand, the fifth layer is more fragile and has fewer stable isotopes. It is thus found that the fourth layer exhibits, at the same time, the greatest flexibility and solidity, as is confirmed by the large number of stable isotopes with a record for the tin element, which is supported by the cubic distributed parietal additions. We can also observe that three elements have many stable isotopes because they form boundary elements between two pentamorphic morphologies. This is the case of molybdenum-42 with 7 stable isotopes because it is the element with the third saturated dodecahedral layer. And, at the same time, it is the first unsaturated representative of the fourth layer. The samarium element 62 also has 2 isomeres because it constitutes both the fourth saturated layer and the first unsaturated element of the fifth layer. The same is true for lead-82, which is the last saturated element of the fifth dodecahedral layer, and also has an isomass in icosahedral morphology, as will be seen. Now let's move on to the particular structures of the parietal reinforcements. They are initially classical as in the middle elements. It is therefore the equatorial type dodecahedra that can be integrated onto the 12 faces of the dodecahedral layers. They fortify the nuclear wall on condition that they distribute themselves in a balanced way. The addition of the triangles to the third dodecahedral layer must also be noted, as they do not constitute a unit of charge when they form only a group of 3. But above all, it is necessary to describe the internal columns formed by a stack of dodecahedra. We saw that they made up the lithium structure because the bond between dodecahedra is not stressed. But these columns were not stable beyond lithium because the centrifugal forces expelled the extremities. Now, in the case of heavy elements, these internal columns can exist and last in time because the ends are enclosed into the wall. They are all the more favored as they participate in the stability of heavy nuclides, as does the umbrella stick or tent pole. Under these conditions, the length of these columns can be measured. It is then seen that, for the fourth layer, a column of 7 dodecahedra in length can be inserted into the structure. Since the 2 ends of 6 pentagons are integrated in the electric charge, there remain 60 internal pentagons, and therefore a mass of 20 units. Thus, from cadmium-116, isotopes with a mass greater than 20 appear, especially in the heaviest. The list of nuclides that can contain internal columns is shown. Now, if the third dodecahedral layer is too rigid to integrate these structures, on the other hand, the fifth layer clearly shows that all its isotopes have a mass greater than or equal to 24. Indeed, the length of the internal column develops on 8 dodecahedra of length, which gives a number of 70 internal pentagons. It should also be noted that the internal column may also have a bulge in the center. The most stabilizing of these bulges is represented by the oxygen core. Under these conditions, this core makes it possible to keep the right column without disturbing constraint with two opposing branches. Now, with a central bulge of the inner column with an oxygen core, we get an additional 96 internal pentagons, and therefore 32 mass units. We can then see in this table that there is a great majority of nuclides of the fifth dodecahedral layer, which has stable isotopes of mass equal to or greater than the supplement of 32. And this internal column structure is important for studying the last nuclear layer of icosahedral morphology.
It was a teenage wedding and the old folks wished him well. You could see that Pierre did truly love the mademoiselle.